Hello, in this video we're going to continue talking about proof techniques. So we're going to talk about proof by contraposition and proof by contradiction. So first let's see proof by contraposition. So in the previous section we've seen contraposition, and so we've seen that P implies Q can be derived from not Q implies P. So it is sufficient to say that if we need to prove P implies Q, we just try to prove not Q implies not P. So let's see an example. So it says prove that if the square of an integer is odd, then the integer must be odd. So here is what we need to prove. We need to prove that n squared odd implies n is odd. So basically we need to prove P implies Q, where P means n squared is odd and Q means odd. So to prove by contraposition P implies Q, we need to prove that not Q implies not P. Since P is n squared is odd, Q n is odd, so we negate Q, which is n odd, became n is even. So negation of Q become n is even. Since P was n squared odd, now not P become n squared even. So you negate and you flip it. So that's what we need to prove. So if we need to prove by contraposition, we just need to prove that if n is even, then n squared is even. Okay, so if indeed n is even, then it can be written as 2m, where m is an integer. Then n equal to m implies n squared equal 4m squared, so I square both sides. So now what we know, if n is even, which is n equal to m, then n squared is also even. As we could see, this is even, and the reason why it's even, because we could write 4m squared as 2 times m squared. N squared is even. So again, if we need to prove P implies Q, it is sufficient to prove not Q implies not P. So what we did here, we started with not Q and we get into not P. So with not Q was n is even, and from there, if n is even, that means the square for it would be n squared equal 4n squared, m squared, which is 2 times m squared. And this is the proof by contraposition. So let's see here proofs by contradiction, which is sometimes called indirect proof. So to prove the theorem P implies Q, here it is sufficient to prove that P and not Q is false. So what I'm saying is, so in the previous section, P and not Q implies false. So this is always false. So false implies anything will be true. So basically this is a tautology, as we've seen in previous section. So hence, as I said, proving P and not Q false implies that we proved P implies Q, implies the conjecture that P implies Q. So what we need to do in here, in this proof by contradiction, you assume that both the hypothesis and the negation of the conclusion are true, and then from that assumption try to get to some contradiction, some things that doesn't make any sense. Once you get to a contradiction, you're done, your proof is done. So let's see an example here. We have proved that if a number added to itself, then the number is 0. So where is P, where is Q? If the number is added to itself, that means this is P. So P become x plus x equal x if the number is added to itself. Then the number is 0. So your conclusion is that x must be 0. So that's what we need to prove. So to prove this simple theorem by contradiction is that what we're going to do, we're going to assume P and not Q. So we assume that P and not Q, meaning that we're going to assume x plus x equal x. This is your P. And x is different than 0. This is not Q. Well, if that's the case, then what do we have? X plus x is 2x equal x. And x is different than 0. Because x is different than 0, I could divide by x both sides. So if I divide x by both sides, I get 2 equal to 1. Hence, a contradiction, because 2 is not 1. And therefore, x plus x equal x implies x is 0. If you add the number to itself, then that number must be 0. So that is the proof by contradiction. So sometimes it depends on the scenario. You're going to see which one fits better. So let's see this example. The sum of even integer is even. What does it mean? If x and y are even integers, then their sum must be even. So right here, this is your P, then this is your Q. So to do the proof by contradiction, we're going to assume P and not Q, meaning we need to prove P, which is x and y are even integers. So we're going to assume x equal to m, y equal to n, where m, n are integers, and not Q. So that's not Q become what? Their sum is not even, and x plus y, it's not even, meaning is odd, And so x plus y odd, meaning x plus y can be written as 2k plus 1, where k is an integer. Okay, so that's what the assumption. The assumption is that 2m plus 2n is equal to 2k plus 1, because the sum of this x and y become 2m plus 2k. The sum of evens, so m and n are even, so if I add them, I must have odd. So right here, if I subtract 2k from both sides, this will be equivalent to stating that 2m plus 2n minus 2k is equal to 1, which is also, if I factor the 2 out, I get m plus n minus k equal to 1. So it tells me that 2 times an integer equal to 1, that means 1 is an even number. And as we know, 1 is not even. So this is a contradiction because 1 is not even. And therefore the sum of even integers is even. Let's see one more example. We need to prove that if x squared plus 1 equals 6, then x must be different than 4. To prove this by contradiction means we need to prove that P and not Q is false. That means we need to assume that x plus 1 equals 6 and x equal to 4, because negating Q is x different than 4, that means it becomes x equal to 4. So if we take x and replace it with 4, we get 4 squared plus 1, or 16 plus 1, which is 17 equal to 6. This is a contradiction. Therefore, if x squared plus 1 equals 6, then x is different than 4. The other proof sometimes used is called serendipity, which is basically not a formal proof technique, but it's fun to know. So let's see an example. 342 players in a tennis tournament, one winner in the end. Each match is between 2 players with exactly 1 winner, and the loser gets eliminated. It says prove that the total number of matches played in the tournament is 341. So 1 champion at the end of the tournament, and therefore we have 341 loser at the end. Hence, we have 341 matches. Hence, 341 matches should have been played to have 341 losers. So this is not, as I said, a formal proof technique, but it's just fun. So here is the summary of all the proofs we've seen so far. So we've seen the exhaustive proof. So we always try to prove if P then Q. So this one you could use it, but as we said before, it may be used only for finite number of cases. When you have the domain is finite, is limited number, you could try. So direct proof is assume P and then you're gonna deduce Q. The standard approach, usually the things to try. Then the proof by contraposition, you're gonna assume the contraposition of P implies Q, which is not Q implies not P. Use this if not Q is a hypothesis seems to give more ammunition than P would. So if you have more, Q not can help you a lot get into not P. So we do contraposition in that case, as we've seen in the previous example. And so the proof by contradiction, I think this is fun as well. So if you need to prove P implies Q, you're gonna do the contradiction. So the proof by contradiction here, we're gonna try to prove P implies Q by assuming P and not Q and try to deduce the contradiction. You get into some contradiction. And you use this when Q says something is not true. So Q, if make it get you to something not true, you do P and not Q and try to see if you get into some contradiction. So serendipity, not really proof technique, just fun to know. I hope this is helpful.